Thank you very much. It's an honor and a privilege to be here. So today I'd like to explain to you some aspects of positive depth Deligne and Lusztig induction and the theory and the developments in this theory. There's been a lot of activity in this subject over the last 20 years or so. And so let me give you first an outline of what I will do. Wait, do I point this here? Oh, point here? Huh? How do I do this? Oh, down, sorry. Okay. All right. So I'll begin by losing my whole audience by telling you the main theorem, but bear with me. But the main point of this talk is actually, my main focus is on section 2 in some sense, which has this funny title, Isomorphisms on Sale. And basically what I'd like to convey is, after explaining a little bit about the context, I'd like to explain a proof technique for proving some certain kinds of theorems, and that proof technique is in this section 2, Isomorphisms on Sale. And then once I explain that, then in section 3, I'll explain how to apply that to give the proof of the main theorem. And then at the very end, I will mention some applications and some future directions. I'll probably only mention some kind of immediate future directions, but yeah, so this is my plan. So there's actually a little bit before I get to section 1. So let me first write down some notation. So unlike many of the talks before me, I work in a local setting, and so I'm not working with number fields. I'm working with local fields like QP, or which I'll call mixed characteristic at various points in the talk, or FP prem T. That's the set of Laurent series where the coefficients are taken in FP. And you can take finite extensions of these, and that's still a valid F. Yeah. Okay. And so I'll give it. Yeah. And then so this is the rest of the terminology. Yeah. So FT, F, G, T, W are very important letters. Okay. So let me begin by reminding you of something that everyone in this room knows very well, which is, here is, roughly speaking, the structure of what QP looks like. So inside QP, the field of p-adic numbers, there's ZP, p-adic integers, and ZP, you can quotient by the maximal ideal of ZP, and you get FP. But of course, when you take this map from ZP to FP, sorry, didn't mean to spoil it, but you lose a lot of information. Yeah, so there will be some empty space. You already saw what I will write here, but yeah. So for Laurent series, the structure is basically the same. So you have Laurent series over here, you have power series over here. By the way, this morning, just to make sure that power series meant what I thought it meant, I Googled power series. It turns out there's an American TV show called Power. And that was the first 3 hits. Okay, so there's again a map to FP, and this map is given by sending T to 0. But again, you lose a lot of information, and how do you gain back the information? Well, up here, instead of quotienting by P, you could quotient by P squared instead. Down here, instead of quotienting by T, you could quotient by T squared instead. So by sending, so you do this, and you can do this for P cube, P to the 4, etc., blah, 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 blah. And okay. And so you can do this in general as well. So for F, a non-Archimedean local field, you have your ring of integers, which I'll denote by OF. And it has a quotient to FQ, but also all of these finite rings. And for me, I work with representations of groups like GLN over F. And for groups like GLNF, there's kind of a similar structure. So when I write G of F, you can think GLNF if you wish, or even GL2F is still interesting. And so inside G of F, you have G of OF. And again, there are these quotients to these finite groups on the right. These finite groups on the right are very important. So oftentimes when we study the representation theory of this, we actually first try to understand some part of the representation theory of G of OF. In general, that's actually a much harder question than the representation theory of this, but we just want to understand some part of it. And to understand representations of this, it's actually enough to understand representations of these finite groups over here. Okay, so I work with geometry and its relationship to this picture. So let me tell you about the geometry related here. Okay, so the oldest case is this first kind of group, something like GLN of FQ. And in 1976, in a remarkable work, Deligne and Lusztig wrote down some varieties, some geometric objects on which this group acts. And basically, one is usually happy when this happens, because if you have a geometric thing on which you have a group action, you can take its cohomology. The cohomology inherits the group action, and now you have a representation. And so that's the basic framework. I actually won't define any of the varieties on this that will appear on this screen. I just want you to have a sense of how it fits into other things. So maybe a small remark about Deligne-Lusztig varieties. Deligne-Lusztig varieties are very close to flag varieties. And the relationship between flag varieties and representation theory is very deep and very established and very interesting. And so it is often a happy word to hear a flag variety, or I mean, for me, also happy to hear Deligne-Lusztig variety. So a few years later, in a very short paper, Lusztig conjectured the existence of a p-adic version of this. And so this happens at the level of G of F. And so, so I'll say, okay. And then much later, he kind of returned to this question and wrote down a definition of a positive depth Deligne-Lusztig variety. And positive depth refers to the fact that this R can become bigger than 0. So you'll note that if R is equal to 0, then that just recovers this classical case at the front here, at the top. Okay. Yeah. So this picture has been studied by many people. And there's also relations between this picture and other kind of p-adic geometry studied by other people. So I just write this down for some context here. So these, for purely representation theoretic questions, the atomic thing to study is this picture over here. Proving something over here has immediate consequences over here and immediate consequences over here. I mean, by immediate, it means like due to work of many people, for example, Alexander Ivanov, who is here at this conference. And so what I'd like to do in this talk is to talk about this work right here, actually, this one right here, joined with myself and Masao Oi, studying explicitly from the perspective of representation theory, these varieties. Okay, so now I come to the main theorem. So here's the main theorem. And so this theorem says the following thing, which is it gives a definitive answer to the question of what does positive depth Deligne-Lusztig induction give you, especially from the perspective of the local Langlands conjectures. The local Langlands conjectures, which I also won't tell you about, but well, I won't say what it means, but it predicts that the representation theory of something like G of F has a very nice structure. There's some arithmetic properties to certain finite collections of these representations. So this here is a finite set of representations, and the claim is that this has really nice arithmetic properties. So not just representation theoretic properties. So over the course of this talk, I'll tell you about kind of what it means to prove a theorem of this type, and what subtleties there are in constructing L packets. So the takeaway here is that from a theta, you can build this kind of representation. This representation comes from this positive depth Deligne and Lusztig variety that I wrote down on the previous slide. Yeah. Okay, so some comments about this is when R is equal to 0, this is a quite well-known story. So it's really the R positive thing that's the new contribution of this theorem. So let me tell you about R equals 0 first. So some comments. So when R is equal to 0, this is you can call this the depth 0 setting. This is also called the tamely ramified setting. If you're a global person and you like to think about modular forms, then this is like I'm working at some prime p, and your level is divisible by p, but only once. And then yeah, okay, so that's this setting. So Deligne and Lusztig is what you already saw. That was 1976. Its relation to representations of p-adic groups was then studied in the 1990s by Morris and Moy-Prasad. Then L packets of these representations was studied by Debacker, Reeder, and Kazhdan-Warshawski in the early 2000s. And then from a geometric perspective, which also obtained a new proof, an equal characteristic, is by Bezrukovnikov and Warshawski using the theory of character sheaves. Okay. So in this setting, actually, the theory comes from geometry. And the reason that is because the only way we, at this point, know how to understand the representations of G of FQ is through representation theory and is through geometry. However, for positive depth, we can do it algebraically. And so that's been the historical approach. So when R is positive, then this I call positive depth. And this is no longer tamely ramified, this is wildly ramified. So in the analogy with modular forms, this is when p to some power divides n. So it's worse. So there's been lots of work on this, and primarily from an algebraic approach by these various people. So it's much more subtle, and I will tell you about these subtleties later in the talk. Okay. So the strategy here is I have constructed some geometric representation, some representation that comes from geometry, and I know that other people have studied it from algebraic perspectives. I want to build a bridge between these two things in order to give an answer to what representations am I getting from the geometry. And so the strategy is to compare these two representations, the geometric one and the algebraic one. And so this leads to a kind of general representation theory question, which is, if you are given two representations, pi1 and pi2, how do you know if they're isomorphic? And so this leads into what I think is the most important part of this talk, which is this isomorphisms on sale. Okay, so I like this topic very much. I hope to convince you to also like this topic. Okay, so let's start really basic. Suppose I have a representation of a finite group G. It's a finite dimensional representation. That means that I'm giving you a group homomorphism from G to GLNC. And what I can do then, and what we learned from representation theory early on, is I can consider its trace, its character. And that's a very nice thing to do. Instead of writing out, you know, an n by n matrix, which has n squared numbers that you have to write down, you just write down one number, the sum of the diagonals. And so why is this important? This is important because of the first miracle of representation theory, which is that even though you only recorded the sum of the diagonal entries, this is enough to remember the entire representation. This is a testament to how much structure representations have. Yeah, so obviously this isn't true for like just a single matrix, right? So I think this is a miracle. And in some sense, this miracle is already an isomorphism on sale, right? It's saying that all you need to understand is this scalar valued function, and it recovers this matrix valued function. Okay. So, okay. But in general, it's not so easy to calculate these characters. And so if you're trying to prove that two representations are isomorphic, it actually might not be so easy to tell whether their characters are the same. And part of that is that when you write down the character of a representation, the shape that that formula takes very much depends on how you came across that representation. So for example, in my setting, I have an algebraically constructed representation and a geometrically constructed representation. Because the source of these representations are so different, even if the formulas end up being equal, they'll have very different shape. So this means that maybe you want to lower the cost. Maybe you don't want to have to pay knowing the entire function in order to do something like an isomorphism. Okay, so to simplify some things, let me assume that pi1 and pi2 are irreducible. These are my representations. So let me give a really basic example first. So suppose you have a cyclic group of order n, then irreducible representations of this cyclic group are just given by homomorphisms from this cyclic group to C star. And a trivial example of an isomorphism on sale result, as I'll call it, is that it's enough to understand where a generator went. If I know where 1 goes, then I know where 2 goes and 3 and so forth. Okay? So I don't need to know the whole function in some sense. I only need to know one value of the function. So it's an isomorphism on sale. So here, next I have a slightly, a little more non-trivial of an example. So this group is called the Heisenberg group. It is a beloved group by many. If you study Weil representation or theta correspondence, then this group comes up very often. And this group has very beautiful representation theory. And an isomorphism on sale results for this group looks like the following. And this is not so hard to prove. You can ask me later if you want to know. So this says that, of course, a priori, you need to know the entire character. However, for the isomorphism on sale, I only need to know the value at this one matrix. So only one value. If I know that this thing has some size that's not p, I realize I need one more thing here. I need not p and also not in C1, not a root of unity. Then one has an isomorphism here. So this is a non-abelian group. This is a non-trivial statement, but not so hard to prove. Okay, so for me, the kinds of groups that I'll look at is things like GL and FQ. And so, and in particular, not groups that look like this or groups that look like this. So what is an isomorphism on sale for such a thing? So let me take GL2 FQ as my example. So if you haven't seen GL2 FQ before, I would like you to think of SL2R in this case, as I go through this slide. And so in this first case, this first example here, this is the diagonals inside GL2 FQ. That's like diagonals inside SL2R. If I take a character on this thing, a very special character, it turns out that there exists an irreducible representation of GL2 FQ that has this very nice character formula. So this says that if I take A, B, C, D with distinct eigenvalues, alpha and beta, then the character formula at these very special elements, these are called regular semi-simple elements, is given by an averaging over theta. So it's quite a simple formula, right? This is like theta plus times plus W theta. Yeah. So this is an averaging. And it's 0 if your eigenvalues were not in FQ star. So basically this says that you take something with distinct eigenvalues, either you're allowed to evaluate your character at those eigenvalues or you're not. If you're not, character is 0. So in general, these character formulas can get quite difficult, and the character table, establishing what the character table of groups like G of FQ is, was an open problem for a long time, because groups like G of FQ occupy one of the 3 infinite classes of finite simple groups, the most interesting class, in my opinion. Okay, so this is the case of diagonal torus. But there's another case as well, as you might expect from a formula like this, which is what happens if you had the opposite thing. Maybe in this first line you have 0, and the second line you have some kind of averaging over theta. And that's this here. Okay? So how to think about this in terms of SL2R is that this first thing is the diagonal thing, and this thing is like SO2 sitting inside SL2R. So that's the analogy here. So over here, we have things like principal series. Over here, we have cuspidal things. And this aligns with terminology from modular forms. Okay. So what's the isomorphism on sale statement? The isomorphism on sale statement is that the most important thing about these representations pi theta is, in fact, this really easy character formula. So I will call this kind of character formula star theta, and it will appear often. But what it means is it's 0 most of the time, and then in a special direction, you're actually just an average of theta. Okay. So here's the isomorphism on sale statement, which says that these formulas that you saw before actually determine the representation. There's only one irreducible representation that has this character formula. And it's an easy character formula. You didn't have to know the difficult part. You only needed this part. And this theorem holds in general. So this is not just a GL2 thing. This is an arbitrary connected reductive group over FQ has this property. Okay. So I wrote lots of attributions here. The first time this was studied was observed, maybe was by Lusztig in 1979 for general case of G of FQ. In 1990, for GLN, p-adic GLN, this was studied by Guy and Yart. And then my collaborator and I, Masao Oi, studied this question for a general p-adic group, and then also for something like G of ZP. And in all of these cases, one has a statement of this type, which is that on some locus, some analog of distinct eigenvalues, it's you have to be a little bit careful in the p-adic case, but for the FQ case, this is actually the correct thing. Distinct eigenvalues, then you have a formula like this star theta, and this uniquely determines the representation. So that means that if you know your representation has this this form, then actually, like, you got the one that I might be holding that also has the form. I didn't have to check elsewhere. Another way to phrase this theorem is that this formula extends uniquely to an irreducible representation of G. So this is like a continuation kind of statement. Like, you should think of it, you know, like you have a continuous function on some space, you take some open dense part of it, you say, oh, I know what the values of this function are there, I can uniquely continue by taking a limit to the boundary. So at the very end of the talk, I will say what that means more precisely. There is a precise sense in which this is a continuation. Okay. So this is our isomorphism on sale. What I want to do is to show you how to use isomorphisms on sale to prove the main theorem. Okay, so again, this is the main theorem. Kind of looks nothing like the thing before, right? But let me try to convince you that it is. Okay, so our starting situation is that I take some character of something like SO2 inside SL2R. And what I've written starting from the statement of the main talk or main theorem is that starting from this data, you can build a representation. You don't know what it is yet. And then I mentioned right after stating the main theorem that there's historically been algebraic approaches to understanding this. So that's this right here. So this t theta is the same starting data as over here. And by work of Tacho Caleta in the last, maybe it was published 2019, so in the last 10 years, one can unwind this t comma theta and build this kind of datum that looks much worse. Okay, so this looks much worse than this, but that's okay. The point of having this is that that there's an algebraic construction of representations of p-adic groups that takes as input this kind of data and spits out some representation. So that's this lower thing right here. So I start with this t theta. I how factorize it to get this form. This form allows me to build a representation. So in both of these cases, we're starting with some character of a torus, and we're ending up with a representation of a p-adic group. So natural question is, are these the same? And actually, the main point of the main theorem is that they're not. Okay, so why is such a thing important? I mentioned before that there are subtleties when you do this wildly ramified setting. And the subtleties are exactly that this lower recipe, this algebraic recipe, doesn't work. It's not compatible with building L packets. And this realization is due to de Backer-Spice in the first case and due to Caleta in general. And so what's the fix here? The fix is that one needs a correction term given by this squiggle here. And this squiggle is actually something quite innocuous. This squiggle is just a quadratic character. It just takes values in plus or minus 1. But that quadratic character messed up everything for a long time. So nowadays we have some better sense of what this is, but I think it's still quite, it's a subtle and mysterious business. Plus or minus 1. Yeah, sign mistakes are not welcome here. Okay. Okay, so what is my task here? Well, before I had isomorphisms on sale, right? Which is, oh, I have to go back quite a few to, oh, quite a lot. Okay, I won't do that again. I want to use this theorem. So I want to prove that my pi1 coming from geometry and my pi2 coming from algebra both satisfy this kind of star theta. Well, of course, they're not both going to satisfy star theta because of this discrepancy, right? So let's prove the main theorem now. In order to apply this isomorphisms on sale result, we need two things. We needed that the representation is irreducible. And secondly, we need this computation on this kind of distinct eigenvalues locus. And so I need both of these data for the algebraic part and the geometric part. And so I can write a chart to fill this in. Once I have this filled in, then the proof is done. So the algebraic side is, let's do the algebraic side first. Why is the representation constructed on the algebraic side irreducible? This is due to work of JKU in 2001. On the geometric side, actually, this took some time to prove that positive depth Deligne and Lusztig induction gives you an irreducible representation. That's somewhat surprising, but it's a subtle business. So it has somewhat long history. And the history of this is that at first it was proved under some kind of extra genericity conditions. And that's the these first three works are under such a genericity condition. Work of Dudas and Ivanov relaxed this condition for certain tori under some assumptions on what you're allowed to induce, what some of the inducing datum is. And in the most general case known right now is due to myself from a paper last year. And so now we know that all the pi's that I'm interested in are irreducible. So that's good. That's one of the assumptions that we need. That's one of the hypotheses of isomorphism on sale. Then we need a computation of what the character is on these special values. And the character, for geometric reasons, is actually quite easy to compute. For some geometric reasons, you use some fixed point formulas. The fixed point locus becomes some zero-dimensional thing. It's something that's easy to calculate. So what we see here is that on the geometric side, the character formula is simply given by this kind of star theta formula. Okay. So what's missing is the algebraic side. This is a somewhat subtle computation, but this is something that Masao and I did a few years ago. And note here that we have this. So that's very happy now, because now we see this correction term up here. And so what's the only way that we have a compatibility between the algebraic side and the geometric side? It's exactly by this difference here, by the correction term that makes the parameterization now compatible with L packets. So in other words, the reason that we know that positive depth Deligne and Lusztig varieties realizes L packets is exactly because the geometry didn't need to be twisted. The geometry knew somehow intrinsically that you needed this twist that you have to carry around. Okay, so before I move on to the last section, I'd like to go back and say some caveats of what might happen with isomorphisms on sale. Like, what can you not get from isomorphisms on sale? So let me go back now. It's quite away, but okay. So this statement, we can leave it here like this. This statement tells you that all you need to know is something about this on some very special elements, things with distinct eigenvalues. But it's also possible for your Q to be so small that this isn't possible. So for example, imagine GL2 F2, right? The only non-zero element inside F2 is 1. So there's no way to have distinct eigenvalues in GL2 F2. So that means that such a theorem cannot possibly hold in this setting. And so this Q is good condition is exactly making sure that you have enough matrices with distinct eigenvalues for this star theta to distinguish. So that's one of the shortcomings of this. However, what I want to point out is that this condition on Q good, I mean, you might think, oh, Q is a power of P, and Q being large, maybe that's like the same as P being large. But I actually want it to be a condition on Q because I can have P really small and just take a really massive power of P. So this theorem, for example, holds for 2 to the 100. Actually, you don't need it to be so large. This Q good, in most cases that I care about, I think maybe like Q bigger than 5 is already enough. So this Q largeness condition is not so serious. Okay, so now I've said something about some subtleties about Q. I want to say some subtleties about P. So you'll notice that in the main theorem, I said for good P and for good Q. I've only told you about where the good Q part comes from. So where does the good P part come from? The good P part comes from this lower line here. in this construction, this only works for good P. This upper part, the geometric thing, works for all P. That doesn't care about P at all. But this lower thing does care about P. And so that's where these two conditions hold. But the one of the advantages of isomorphisms on sale is because it's purely a Q-theoretic condition, it means that whenever it is that this lower line is boosted to also contain some small p's, one can perform isomorphisms on sale to try to understand the comparison between the end results on the right. Okay. So let me spend some time on applications. Okay, so the first application is what I said already. In this kind of complicated diagram, but mainly the thing to remember is that I have F, I have the ring of integers of F, and then I have these quotients of the ring of integers. Then I have these three geometric objects, these classes of geometric objects, and they're very closely related to each other. Due to very interesting work of various people in geometric directions, one knows that proving representation theoretic results on this side results in representation theoretic implications here and representation theoretic implications here. So that's the first kind of application. And I'll spend the rest of the talk talking about some other kinds of applications. So let me just read this here. So in general, character formulas for representations of p-adic groups are super hard and super subtle. And if you've ever opened up such a paper, then you'll note like this is something where, you know, it can take one whole page to state the theorem kind of thing. When you study arithmetic properties of L packets, when you study the behavior of the representations in some kind of orbit, one way to do it is to try to understand these very hard formulas, take averages of them in some particular way, and to then study the averaged out formula. But what the main theorem tells us is that another way to possibly do this is to use the geometry to study these properties instead. And what that allows us to do is to say, instead of understanding one formula at a time individually, maybe it's enough to just understand the average of all of them, which in general is a much easier thing, as we know. And so what the main theorem allows us to do is it gives us hope that we can study predicted symmetries of L packets using geometry. And a key point of this is that the geometry didn't need this extra twist, right? The geometry somehow knew about everything to begin with. And so we should be able to spin that to our advantage. And so I'd like to present one more theorem. This theorem is due to, well, in the R = 0 case, this is due to Lusztig. And in the positive case, this is recent work by myself and Roman Bezrukovnikov. And the statement is like this, is that this positive Deligne-Lusztig induction, these representations, this will give me a representation of something like G of FQ for all Q. But you can take this Q and you can take powers of it, and you can ask whether there's some symmetry to that family, so whether there's some structure to that family. And the answer is yes. If you let that power of Q go to infinity, then in fact, all of these representations can be packaged together into a geometric structure given by something called a perverse sheaf. So this was a remarkable breakthrough of Lusztig in the 1980s when character sheaves were first defined, and in 1990 when it was shown to have good relations with Deligne-Lusztig theory. Yeah, okay. Now, since I have a little bit of time, maybe I can say a little bit. Let me think. I'm trying to organize the various things that I could say into something coherent. Okay, let me just leave it at the following thing, is that, so in general, this constructing nice, simple perverse sheaves associated to algebraic groups is a very difficult venture. It's something that's well studied for reductive groups, things like GLN, and it's also well studied for things like upper triangular matrices, unipotent groups, and it's also well studied for things like not just unipotent upper triangular matrices, but upper triangular matrices, so like solvable groups. But in general, there are lots of algebraic groups that don't fall into one of these camps, and it's very difficult to understand what a theory of character sheaves might look like. And the contribution of this work here is in picking out a particularly manageable class of algebraic groups that have strong ties with representations of p-adic groups and studying the character sheaves that occur there. And so this, for example, gives a crucial ingredient to studying now wildly ramified character sheaves on loop groups and giving geometric ways to understand wildly ramified behavior in local Langlands. Okay. So let me let me give this next talk and then next slide, and then maybe and then I'll decide what to do. Okay, so let me give 3 immediate takeaways of combining both this last theorem, this geometric theorem about perverse sheaves, and the previous theorem about varieties. So the first thing is this thing that I talked about during the second part, isomorphisms on sale, which is that I said another way to phrase this isomorphisms on sale is that if I just take this function on the distinct eigenvalue part of my group, and I let it equal to this formula star theta, then the assertion is that this function can be uniquely continued to a character of an irreducible representation. This kind of process is not a representation theoretic notion. This is I would call it an analytic notion. It's a way to continue outside of some locus. And so, but of course, like if you're in a group like G of C, GL2 of C, then continuity actually makes sense because you have so many numbers in C. But for something like GL2FQ, it's a discrete thing. You only have finitely many points. So what does it mean to have a continuous function there? Well, there's a geometric answer, which is that, as I've said, this notion of GL2FQ, actually we can build it up into a family where it knows about GL2FQ squared, GL2FQ cubed, GL2FQ to the 4, GL2FQ bar. And by doing this, we've created something that has more numbers. And with more numbers also comes geometry. And so the notion, the kind of analytic notion of continuity, of like taking a limit to a point outside of your locus, has a finite field version, which is given by this geometric notion of intermediate extension. And so this notion of intermediate extension is closely related to these words, perverse sheaves. And so for this reason, this theorem exactly tells you that that characters of things like G of FQ are continuous in the sense that they are determined by this open locus and you can figure out what the remaining values are by taking an intermediate extension. The second immediate takeaway that I wanted to mention is that this combining these two theorems allows us to establish something called the positive depth Springer hypothesis. So what is this? This provides for you a geometric explanation for the appearance of orbital integrals in character formulae. So I told you on the previous slide that representations of p-adic groups have very difficult character formulae. And basically one of the main reasons for this is the appearance of orbital integrals and having to deal with having to deal with convergence problems and this kind of thing. But by putting these representations in a geometric framework, actually it's very natural to see why there are orbital integrals in this. The perverse sheaf framework allows you to see that these things are very close to Fourier transforms of orbital integrals, things that are supported on one orbit at a time. And the last thing, that immediate takeaway that I wanted to mention, is this result of Bezrukovnikov and Warshawski that I already mentioned on a much earlier slide. So in the tamely ramified setting, R equals 0 setting, Bezrukovnikov and Warshawski were able to utilize Lusztig's theory of character sheaves in order to prove very interesting endoscopic character identities for L packets, for depth 0 L packets, for tamely ramified L packets. So one such thing is called stability. And so that's why I wrote stability here, but actually they can do it for arbitrary endoscopic character relations. So what happens if you want to try to do this in the wildly ramified setting? Well, the starting point for Bezrukovnikov and Warshawski's machinery was to start with Lusztig's theory of character sheaves, then to build something on the p-adic group, and then study that resulting object. But that then means that you need some kind of wildly ramified character sheaf theory in order to feed in as the starting datum. But luckily, because of the work because of the theorem that I just stated of Bezrukovnikov and myself, we now have that. And so we now have this input data. We have the step 0 of a program that we can try to run. So a question that's ongoing right now is the question of, for the positive depth setting, in other words, the wildly ramified setting, can we combine the new character sheaves of Bezrukovnikov and myself with this technology in order to prove endoscopic character identities for wildly ramified L packets. So this is ongoing work. To see more about this, maybe ask in 1 year or 2 years. Okay, actually, I'll stop here and then maybe just take questions and go based on that. Thank you.